Hey, what's going on, students? This is going to be a mini lab where I'm going to show you how I can stack water. And the only difference is going to be its temperature. So we've been talking a lot in class about density, we've been talking a lot about ocean currents, and this is going to be an opportunity for you to show your teachers, aka this guy, what you have learned about the flow of ocean currents and how temperature and density affects those. Let's go. So let's first get started with talking about ocean currents. The current is very, very important because it's the mass of the water moving from one place to another. And the water in the ocean is always moving. It's always being pushed back and forth. And the temperature differences between the equator and the North Poles affect the way that the water moves. Also, our planet rotating creates what's called the Coriolis Effect. There's a video on the page of me reading an article about the Coriolis Effect and how the rotation of the Earth around the sun creates the movement of water and the way that it moves. So it's very, very important because it moves organisms around the ocean as well as moving the hot water and the cold water, which affects both the environments on land and in the ocean. And it helps move around things like plankton, and it can carry eggs and larvae of organisms that have external fertilization. But it also moves the food around, which causes the animals to move around. And the complexity of the ocean's ecosystem and the food chain and the food web in the ocean is very, very complex. But it also carries away pollutants and moves those around. In class, we talk about the rubber duckies that fell into the ocean in the Pacific and floated all the way around the world for years. There are three types of currents. There's surface currents, there's circulation currents, and there's currents that are driven by the wind. And that also plays into upwelling. Surface currents, wind-driven currents. Now, this is just the top 100 to 200 feet of water in the ocean. And these obviously affect the water on the surface. And these are considered horizontal currents. And it's caused by the friction between the wind and the water. So us in Ohio, we're nowhere near an ocean. But if you ever go to Lake Erie or to one of the lakes here in central Ohio, like Buckeye Lake, you can see that the top layers of water are being pushed in the direction of the wind. So the next time that you're at a lake, look up at a flagpole or throw some grass into the air and see which way it blows, and see how that is blowing in the same direction as the water on the lake. Surface currents are also affected by the Coriolis Effect, and this causes moving objects in the northern hemisphere to veer clockwise. And then objects in the southern hemisphere go counterclockwise. There's a really cool video that I'm going to show you here in just a second that shows in the northern hemisphere, water going around in a bowl goes clockwise. And then they take that same bowl across the equator and it makes the water go counterclockwise, which is super neat. It's also the reason why in the northern hemisphere, your toilet water, when it flushes, it always goes clockwise. If you were sitting on a toilet in the southern hemisphere, it would go counterclockwise when you flush it. If you don't believe me, check it out.
clockwise when you're north, but if you go
Yes.
south, it will be the other way around.
It's going clockwise now because we are on the north hemisphere. This is the water, the flower is going clockwise. See how it goes? You can see it is now going anti-clockwise.
Then on March 21st,
So that's why, on March 21st
and September 20th,
zero latitude.
where you won't see clockwise, you won't see anti-clockwise.
Okay, as you can see now, the flower is not moving at all.
It doesn't.
So, for the Coriolis effect, it's all caused by the Earth's rotation. And objects deflect to the right in the northern hemisphere, and objects deflect to the left in the southern hemisphere. And this creates gyres. A great example of the gyre is the eastern coast of the United States and the western part of Africa. You'll also see that a lot of the hurricane paths start here in Western Africa, and they blow right across near the equator, and then they pick up steam and they just hit Central America, the islands, Bahamas, Dominican Republic, Haiti, Cuba, and they can get sucked into the Gulf here, or they push right up the Atlantic coast and go back into the ocean. But these are massive circular systems of wind driven by surface currents. And you'll notice when you look at currents maps that in the northern hemisphere, they are always going clockwise and counterclockwise in the southern hemisphere. So we can see that on this map here. Here's the United States. Here's Columbus, Ohio, where all of my students are sitting watching this video, happy as a clam to be hearing my voice over the computer. Oh, it's a great day, isn't it? So this one is going clockwise. Okay. This one also going clockwise. And your equator is drawn right through here. And in the southern hemisphere, you can see that all of these ocean currents down here are going in a counterclockwise fashion. And this creates eddies, warm rings of water movement, and they break off of the currents and transport organisms elsewhere. So eddies are these little circular patterns of the water, and this is caused by just spinning off from the main current. And then you've got circulation currents, and this causes deep ocean circulation. We also refer to these as vertical currents. The temperature and salinity, which means salt, for those of you following along, salinity means salt, cause water density to be different. Due to the density differences, water masses rise and fall. So when we look at the Arctic, where there's tons of glaciers and ice, we have newly formed ice sitting up on top, and the salt is released down into the ocean, and it sinks and then it pushes down. So that denser, saltier water sinks very, very quickly and then pushes out and away towards the equator, which would be located way over here. And fresh water pushes in the northern hemisphere towards the north, and we'll display that for you when we see how this cold, denser water sinks and drives down to the bottom. So circulation currents, when we combined with surface currents, results in a conveyor belt of movement of water around the globe. So the water is constantly flowing, and this warm water is going to push up towards the Arctic, and the cold water is going to get sent back down towards the equator. And as the wind blows, it moves water away from the shoreline, and it causes new water to rise up in its place. And as that water gets pushed up towards the surface, these vertical currents that we call upwelling bring a lot of minerals from deeper parts of the ocean and push them up towards the shore. And here's a great diagram of that. This upwelling is pushing up the coast, so like you'd be standing here on the beach, wind pushing out over the water, and it's going to push that water back towards the ocean. And it'll get picked up by the current, and it will help circulate it around. So this experiment is really, really simple. All you need to do at your house is get a large plastic tub. It can be a tote box. It can be anything made out of plastic that can hold water. And then you need blue food coloring. You need red food coloring, a cup of hot water, and a few ice cubes. And that's all you need for the experiment. So I'm going to show you what it looks like. If you don't do it at home, that's cool. If you want to, I think it's pretty cool. You can show your little siblings and they'll be like, whoa! I'm going to take an ice cube, and this is going to represent the glaciers and the coldness of the north up around the Arctic. I've put one ice cube in at this end, and I'm going to drip the food coloring directly on top of it and watch what the food coloring does. Notice how fast it's sinking to the bottom at this end. And it's continually going to push down and down and down and down and down because, I don't want to tell you that part because that's the answer. And then at this end, I'm going to add my hot water, and we're going to see how that behaves. You can see the hot and cold now moving towards each other. And that cold blue water, that ice cold water, is pushing down, and it's going right underneath the hot water, and the hot water is pushing up towards the top. And that's exactly how the currents behave in the ocean. That hot water from the equator is going to sit right up on top. And that cold water is going to push underneath. It's not magic. It's science. Just fascinating to look at. Love it. Love science. Oh, it's the explanation of how everything works in the universe. Ah! Okay, now that you've seen the experiment and how it worked, take this time to do a reflective writing piece. And you need to include key terms, including surface currents, deep ocean currents, and density, and describe how the density of both types of water caused them to behave the way that they did. Also, feel free to include a diagram showing the density of the water and what causes it and the reason why it causes it to behave the way that it is. It's kind of hard to talk about without giving away answers, so. All right. I look forward to reading all your writings. Stay tuned for more videos. Also, check out the YouTube channel, Mr. Spoonie's Classroom. And for my students, I will see you in class. Stay safe out there and wash your hands.